Now, I'm going to give you a minute to write down the numbers 5, 6, and 7, because I feel like you need to have these down, even though they're an extension of the ones that are up here. And since I'm not doing numbers 1, 2, 3, 4, 5, and 6 with you, I had a little room to write that. You can put them over on the end if you did the video problems with Dr. Taylor. Okay, so I'll read those out to you just in case you can't see them. So these are just, and I'll go through them as we talk about it. But number 5 is an extension of number 2. So I want to talk about those as we go through, okay? So number 5 says the derivative dx of the natural log of f of x. Okay. So if you notice, number 2 is just the natural log of x. So what if x is a function? So that's all that is. So the derivative of the natural log of f of x equals the derivative f prime of x over f of x. Okay. So we'll go through those and talk about that in a minute. But it's exactly what this says, but I think this makes more sense when we get to those. So the derivative of the natural log of f of x is the derivative of f over f. Okay? All right, so that one is the extension of number 2. Okay, number 6 is the extension of number 4. So number 4 says the derivative of e to the x, just plain old e to the x, is e to the x. Can't get much easier than that. So the derivative of e to the x is e to the x. However, if you take the derivative of e to the f of x, so in other words, what's up in your exponent is something other than x, it's another function, well then the derivative of that is e to the f of x. So basically the derivative of e to the anything is e to the anything, whatever you have. But then you also have to take the derivative of the exponent because that's another function. So it's just like a chain rule. Okay, so the derivative of e to the f of x is e to the f of x times f prime of x. Okay. All right, and then I added, you can see I whited out and added one more. So number 7 is kind of the extension to number 3. Okay. So if you have the derivative of a is a constant, so like 7 to the 5x or 3 to the 2x plus 1. So a is a constant, not x. So if you have the derivative of a constant raised to a power, but that power is another function, then again, the derivative of a to the f of x is a to the f of x. Then you have to do the natural log of the base. And then you can't forget to do the derivative of the exponent. So these are just chain rule problems, but that's the way they look as far as the formulas go, the shortcuts. Okay? All right. Everybody good with those? So also up at the top, where it says the title of the section, Derivatives of Exponential and Logarithmic Functions, I wrote a little piece here that when you're taking the derivative of a logarithm, if you can expand it, go ahead and expand it first. It's much easier. When you have your rules for logs, and you can take a hard division problem and turn it into 2 simple problems that are subtracted, it's much easier to do those derivatives. So with logs, if you need to, expand them first, and we'll do, I think, 1 or 2 of those as well today. And then don't forget, as always, all your other rules apply. Chain rule, product rule, quotient rule, all of those things we will still apply when we're taking derivatives today. So today is all about learning these new derivatives and combining them with what we've done in the past, okay? All right, so let's look at numbers 1 and 2 just real quick, because I always like to do this because a lot of you forget the derivatives of logs and bases that are not e. So if you look at 1 and 3, the base, which is the letter a in both of these, is a number. So like log base 3 or log base 7, or on this side it would be 5 to the some power. Okay, and these are exactly the same as 2 and 4, except on 2 and 4 the base is e. So a natural log is a base e, and obviously the base over here on number 4 are e's. Okay. Well, when you take logs of base e, you're talking about natural logs, whereas when you take logs of other numbers, it's a log. Okay. So the only difference is the the way it's written. I mean, they're still all logs. But look at the difference between the derivative of a log of a base number versus the log of base e, okay? Why does this one look so much harder than this one? So I just want to explain to you, because this natural log of a, okay, is really here. You just can't see it. So any logarithm is 1 over whatever you're taking the log of, okay? So this is 1 over x, because there's an x there. And this would be a log, so it would be 1 over x, right? So that's the same rule. But notice down here it has the natural log of the base. Natural log of a. So again, natural log of 3, natural log of 7, whatever's there. But what is the base here? Well, it's e, right? So really, this problem, if I want to write it, is 1 over x times the natural log of the base. But what is the natural log of e? You guys remember that? It's 1, right? So if you're doing the natural log of e, you don't have to write it because the natural log of e is 1. So that's why that natural log piece goes away when you're doing e's, okay? So the rule is exactly the same. It just looks different because the natural log of e is equal to 1. So x times 1 is just x. So I want you to see that because you guys forget this a lot. Same over here, okay? Look at a to the x versus e to the x. So I'm talking about 2 to the x versus e to the x. E is a specific number. So the derivative of any base to the x power is that number is that problem. So the derivative of a to the x is a to the x. Derivative of e to the x is e to the x. Well, why is there a natural log of a? Because you always have to take the natural log of the base for any logarithm. But what is this natural log? Well, the natural log of e, well, the natural log of e is 1. So I don't really need it down there. So again, exact same formulas. So don't forget that you always have to tack on the natural log of the base. It's just that when the e is involved, the natural log of e is 1, so we don't have to put it there, okay? So I just want you to see that because a lot of you will miss problems like 1 and 3. You get 2 and 4, those are kind of the easy ones, but there's still that log there, okay? We just don't write it. All right. So that's enough explaining of all of that. So let's go do some problems now and practice all that. Does anybody have any questions on that? Okay, so hopefully that helped a little bit, maybe. All right, so we're going to jump to number 7. So this is one of those new rules I put up there, which was number 5, okay? So I'm going to do it this way. So that's what we're ready to do. So we have the natural log of a function. So the very first rule, the number 2 rule, is the natural log of just x. So the natural log of just x is just 1 over x. But if you have the natural log of anything else, then that derivative is, so we're going to have a fraction, and on the top you put the derivative of the inside. So the derivative of x cubed is 3x squared. And then you put the function, the whole function, on the bottom, okay? Because it's 1 over whatever's in parentheses, which is the function itself. And then think about the chain rule. Then you got to multiply by the derivative of the inside. So instead of putting times 3x squared over here, you just put it in the numerator. That's where it will go. So the derivative goes on top. The function goes on the bottom, okay? So that's your derivative. All right, number 8 is one where I have a natural log, but it looks complicated. I don't want to do 1 over this and then do the derivative of this. I mean, that's a chain rule with a radical and a quotient rule. That's a lot of work to do. But since there's a natural log sitting in front of here, I can expand this, okay? So anytime you have a complicated problem that's a natural log, we're going to use our rules to expand it. So I'm not taking the derivative yet. I just want to expand this thing and make it easier on myself, okay? So this is still f of x. This is not a derivative yet. All right, so I'm going to rewrite that as the natural log of 4x minus 6 over x plus 1 to the 1/2 power, right? That's the square root. Okay. All right. So the first rule for expanding is take exponents and move them to the front, right? So I'm going to expand this by bringing the 1/2 out front So that'll be the natural log of 4x minus 6 over x plus 1. Okay. And now I can expand the division problem. I can break that up into two logs being subtracted, right? If you're dividing logs, you can subtract. So leave the 1/2 out front. So I'm going to do the natural log of 4x minus 6 minus the natural log of x plus 1. That's what I want to take the derivative of, because now I got two easy logs to take the derivative of. I don't have to do any quotient rules, anything. Okay, so that's not a derivative yet. That's just f of x. I'm just working on expanding. Expanding is much easier than taking derivatives of harder problems. Might take you a few more steps, but it's still easier steps. Okay, so we're ready to do the derivative. We're going to leave the 1/2 out front. That's constant. So f prime, 1/2. All right, now, just like we did in number 7, we're going to take the derivative of the natural log of this function, 4x minus 6. So the derivative of this goes in the numerator, this function goes in the denominator, and that's it. So the derivative of the natural log of 4x minus 6 is 4 over 4x minus 6. Okay, derivative on the top, which is just 4, the whole function on the bottom. Bless you. Minus. We're going to do the same thing with the natural log of x plus 1. The derivative goes in the top, this function goes in the bottom. So the derivative of x plus 1 is 1 over x plus 1. And that's it. That's a lot easier than doing a big old chain rule with quotient rule and all that. So always use your rules for expanding first, but you have to have a natural log in the problem. If there's no natural log in front of that problem, you'd have to do it. I mean, that's just a regular problem then. Okay, but that makes it a lot easier. So those log rules are nice. Finally going to come in handy. Yes?
On a test, would you have to take the 1/2 and then expand it out or like push it over? Is it fine?
You could leave it just like that. If it was multiple choice, the 1/2 might be multiplied through, so it would become, this would be 2 over 4x. Okay. So you might just have to find the answer in a multiple choice, but if it's free response, you could leave it just like that. Some of you guys would bring the 1/2 through first, like before, like this step, you would do 1/2 of this minus 1/2. That's okay. Yep.
If it's just a log base 10, you can't split it up either.
If it's log base 10, no, you can do that. Yep. All logs have these same properties, so it doesn't matter what the base is. You can always expand. Typically in calculus, you guys are dealing with natural logs because that's just a more useful in real life situation number that we use. So log 10s and natural logs are usually the ones you guys will have. Okay, anything else on that one? All right, let's look at number 9 then, a product rule. 5 square root of x, so that's your first function, times e to the 2x. So you got two functions, we're going to do a product rule. Plain old product rule, but now we have a new, our e's over here. All right, so we're going to start with the derivative of the first function. So derivative of 5 squared of x. So let me rewrite this. So that's 5x to the 1/2 times e to the 2x, right? That's what we're doing. If that helps you. You don't have to change it, but. All right, so 5 squared of x is really 5x to the 1/2. So that's what we need the derivative of. So we're going to start with the derivative of that. So that would be 5 times 1/2. So that's 5/2 x to the negative 1/2, right? Subtract 1 from your exponent, times the second, leave it alone, plus, and then we're going to reverse it. We're going to do the first, leave it alone. All right, now, times the derivative of the second. So the derivative of e to the anything. I don't care what you take in the derivative, e to the anything, the derivative, you start with e to the anything. So the derivative of e to the 2x is e to the 2x. And then you have to take the derivative of the exponent. So what is the derivative of 2x? 2, and it's a base. It doesn't go in the exponent. That's the f of x. I'm going to cover it up for just a minute. That's this piece right here. So it's e to the whatever times the derivative, which goes down in the base. It's not part of the exponent, okay? Some of you make that little mistake. All right, now that's fine. Well, let's say we were going to clean this up for multiple choice. Could you find this answer using radicals and all that stuff? So what would this look like cleaned up? But this is fine for if it says just find the derivative, don't clean it up. All right, so let's look at this problem. In the numerator, you have the 5 and you have the e to the 2x. And then what would be in the denominator would be the 2, and then the square root of x would be in the bottom, right? So I could write this as 5e to the 2x over 2 square root of x. That's what that would look like, cleaned up. And then the second piece, everything's in the numerator, but we can clean it up a little bit. 5 times 2 is 10. E to the 2x, and then I'm going to just write the square root of x at the end. It doesn't really matter. You can put the square root of x after the 10. I just like to write radicals at the back because sometimes it looks like other pieces are under the radical that aren't. But that one, that's all you could do for that. So either of those are okay answers. You just need to start being able to see them cleaned up a little bit. Okay. All right. Number 10 is a log of a different base. So the same rule for natural log. So let's think about what that rule is. What if that was a natural log? If that was a natural log, what would we do? We would put the derivative on the top and the function on the bottom, right? Same thing. Derivative on the top, 10x, the function on the bottom, but we have to multiply by the natural log of the base because now the base is not e. So we've got to add a natural log of 3 in the denominator. So again, for a natural log, we'd have that natural log of e sitting right there, but we don't need it. But it goes in the denominator, not in the numerator. Okay, that's your number 1 over here. That's this one. So you do the same thing, but you got that natural log of the base in the bottom, okay? So don't forget those. All right, that's it. Can't do anything with that. All right, number 11 is the same thing with your exponential function. So number 11 is like the new number 7 I wrote down there, which goes to number 3, if you're looking at the rules. Okay? All right, so this is not e to some power, it's 7 to some power. Same rule. Okay, same exact rule. So the derivative of anything raised to a power is anything raised to that power. So 7 to the 5x. So we start off with the original function. But since the base is not e, we have to tack on the natural log of the base. And then what? Derivative of the exponent, because that's a function right there. So what's the derivative of 5x? 5. Now, that is it. You can't make this 35. You can't make that 35. You can't multiply an exponent and a log and a number together. Those are all separate things. That's all you can do with that problem. Okay? So you know when I say leave it alone, it's your best bet because you want to start cleaning up and you might do it wrong. But logs and exponents and numbers are different. You can't add them together or multiply. Okay? That's it. So e to the anything, any number to the anything, you start with the derivative of it, which is that whole thing. If the base is not e, you need that natural log piece, and then the derivative of the exponent. Okay? All right, number 12, natural log. So if it's a natural log, I'm going to have a fraction. What goes in the top? The derivative of what's in here, and what goes in the bottom? What's in there. So it doesn't matter what's in there. All right, so I'm going to put the derivative of cosine of x in the numerator. So the derivative of cosine, negative sine, and you put the function in the bottom. And that's it. Okay? So that's the natural log. You could write that as negative what? Sine over cosine? Tangent, in case it's cleaned up, right? So that's a tangent problem. You could write it either way, doesn't matter. Okay, so any natural log, derivative of what the function is in the top, the actual function in the bottom. All right, now number 13 is a little bit backwards because your outer function is sine, not natural log. So this is a chain rule where we do the derivative of the outside first and then the inside. Okay? All right, so we're going to start with the derivative of sine, leave the inside alone. This is a chain rule. So the derivative of the sine is cosine. Leave the inside alone. Now times the derivative of the inside. And the derivative of the natural log of x is just 1 over x. That's its derivative. And that's fine to leave it like that. If you want to clean it up, all you could do is write it all together as one fraction. You could do that, but you don't have to. Okay? All right, 14 is a product rule. Cosine of 4x times the natural log of 3x. So that's a product right there. Cosine of 4x times the natural log of 3x. So we're just going to run through and do a product rule. So we're going to start with the derivative of cosine of 4x. So the cosine of 4x, this is a chain rule. We're going to start with the derivative of the outside. So the derivative of cosine is negative sine, leave the inside alone, times the derivative of the inside, so times 4. I guess I shouldn't have put that other parentheses there, but all right, so that's all the derivative of the first term. And you can write negative 4 sine of 4x, that's fine. Most of you know to do that now. Okay, so there's the derivative of the first times the second, leave it alone, natural log of 3x, plus the first, leave it alone, cosine of 4x. And now we need the derivative of the natural log function. Okay, so the derivative is the derivative of a natural log. Derivative goes on top and the function goes on the bottom. So the derivative is 3, function is 3x. Now I'm fine with you leaving like that. However, if this was cleaned up, you would have cosine of 4x just over x, right? Because those 3's are going to cancel out. But that's okay to leave it like that for me. But if it was multiple choice, you'd probably cancel those 3's out. Yes?
We wouldn't have to add on the derivative of 3x.
That's right there. So let me,
Oh, okay.
so yeah, and I want you to see this because I don't want that to throw you off. So here's what we're doing, the natural log of 3x. Oops. So the derivative of the natural log of anything is 1 over the anything. So you really start with that, and then you do times the derivative of the inside, which is that. So what I'm saying is instead of doing this step, we're just going to keep the derivative, because it's always a 1 on the top. So that's the same as the 3 over the 3x. So that's the way that I look at it, just to make it easier to kind of write. But if this makes more sense to you, then do that. So like that first one we did, I don't even remember what it was. You know that one? So we did the derivative on the top, the problem on the bottom. Well, you could do the derivative of natural log, 1 over 1 over that, and then times the derivative of the inside, whatever it is. So we're just putting it in the top, okay? So you can do it either way. Losing my voice. All right, number 15. So I'm just looking at number 14 real quick because this side you really can't clean up much. I mean, you can write this as negative 4 sine of 4x natural log of 3x, but that's all you could really do there. And in this one, you can get rid of the 3's. So if you were cleaning it up, not a whole lot to do on that one. All right, 15 is just e to a function, but look at the function. The function is a product, x times the tangent of x. Okay, so we got to do a product rule when we do the derivative of that exponent. All right, so the derivative of e to the anything is e to the anything. Always start with that. And then we have to do times the derivative of the exponent. So now we have to do so we have, our 4 things we're getting ready to do. Product rule. Hope I left enough for doing it. Okay, so derivative of the exponent. X times the tangent of x. Product rule. So we're going to start with the derivative of the first term. So the derivative of x is 1 times the second, which is the tangent of x, plus the first, which is x, times the derivative of the second, derivative of the tangent, secant squared. And you can leave it just like that. And you can get rid of some of those parentheses, obviously. Okay? So you're going to be using these new rules along with a lot of the older rules. And on Monday, we add to it our last of our derivatives, which are our inverse trig functions. All the inverse trig functions have their own derivatives. Those are about memorizing pretty much. And their rules are a little harder than these. So get these down now before Monday, because we got more to learn on Monday. All right, so the last page is on logarithmic differentiation, and I wrote a bunch of stuff here, so I'm going to let you write it down. I'll go through it with you. So what is logarithmic differentiation? Okay, so up at the top, this process that we're going to use, you must. So there's two things, okay? 2 points. So you must use this process. You have to. There's no way around it. So what I'm getting ready to show you, you have to use this process when the variable x, that's our variable, when x is in both the base and in the exponent. So if you have the variable x in the base of your problem and as an exponent, you must use logarithmic differentiation. There's no other way to take a derivative without it. Okay? So if you look at number 16, y equals x to the square root of x. There's an x in the base, there's an x in the exponent. So that would be, we have to do what we're getting ready to do. So that's the ones you must use. You may use this, so you don't have to. You may use this for a very complicated function like number 13. Because if I ask you to take the derivative of number 13, you could do a quotient rule, and then when you take the derivative of the top, you would do a product rule. It would be very long, but you could do that. So you don't have to use logarithmic differentiation for number 13, but I am going to because I think it's easier. So I'm going to show you how to do that. So that's the 2 bullet points. So use it for sure when you have variables in both the base and the exponent. You don't have to do it, but try when you have a complicated problem. All right, so then I've got the steps. So let's go ahead and write those steps down if you like steps. If you don't like steps, don't write them down. I'm going to give them to you anyway. All right, so 5 quick steps on this one. So if you're going to use logarithmic differentiation, step 1 is to take the natural log of both sides. Always. Take the natural log of both sides. Step 2 is to expand the right side using your log properties, so like we did on that one problem before. So number 2, expand the right side using your log properties. I'm glad these steps are short. Step 3, you're going to differentiate implicitly because you got y's in your problem. So you're going to use implicit differentiation. So step 3 is to differentiate implicitly. And as always, what you do when you differentiate implicitly, step 4, you'll be solving for dy dx. We already know how to do that. So step 4 is to solve for dy dx. And step 5, the piece some of you forget, you must replace the y in your problem with the original function. So steps 1 and 5 are pretty straightforward. The work is in the middle, 2, 3, and 4. So we're going to go through. I'm going to number these steps as usual just to help you guys out. You don't have to, but just so if you go back and look at it. All right, so remember, we must use this process for numbers 16 and 17. Why? Because we have an x in the base and we have an x in the exponent. We don't have to do it for number 13. You can choose to do it the old way, or you can do it this way, whichever you find makes more sense to you. Okay. So are we ready? All right, so I'm going to go through these, and I'm going to put the steps. So for number 16, the first one, step number 1, we're going to take the natural log of both sides. So we're going to do the natural log of y equals the natural log of x to the square root of x. Okay. Step 2 is to expand the right side. The left side on every problem will look identical because every problem is going to be y equals. So you always have the natural log of y on the left. All right, so step 2 is to expand the right side. So we have an exponent, so we're going to bring it out front. So we're going to write this as the square root of x times the natural log of x. Okay, so that's the expanding part for this one. That's all I have to do. So now I have both my x's in the base, which is now I can do derivatives. So I'm going to do a product rule. Now I can work with that. I just can't work with that. Okay? All right, so that's step 2. Step 3 is to differentiate implicitly. So we have the natural log of y instead of the natural log of x. So the derivative of natural log of y is 1 over y. But since it's not an x term, dy dx. All right? So anytime we don't take the derivative of an x term, we've got to tack that on. And on the right side, we're going to do a product rule. So we have the square root of x, that's x to the 1/2, times the natural log of x. So product rule. So the derivative of the square root of x is 1/2 x to the negative 1/2. Okay, just derivative of the first term. You can write 1 over 2 square root of x if you guys are getting the hang of that. Times the second, leave it alone. Plus the first, leave it alone. Square root of x times the derivative of the natural log of x, which is 1 over x. Now, since I am solving this, I'm going to go ahead and clean up the right side just a little bit. So leave the left side alone for a minute. So we have, again, in the numerator, just the natural log of x. And in the denominator, you're going to have the 2 and the square root of x. So that first term is the natural log of x over 2 square root of x. Plus, and then the second term is just the square root of x over x. So again, if this was a multiple choice, it's going to be cleaned up a little bit. All right, so what do we have to do to solve for dy dx in step 4? How do we get rid of 1 over y?
Multiply by y.
Multiply both sides by y, right? So I'm going to multiply this side by y, which will get rid of it. So I'm going to multiply this side by y. So dy dx equals the natural log of x over 2 square root of x plus square root of x over x times y. So we solve for dy dx. So that is your answer, except the problem started off with just x's, so we have to end the problem with x's. So that's step number 5. Can't leave y in your answer on the right side. So you're going to replace that y with the original function, which was x to the square root of x. So our last and final answer, our derivative of this problem, is the natural log of x over 2 square root of x, square root of x over x, times x to the square root of x. Okay, so there's your answer. So these are not, typically, they're not too hard of problems to do. It's usually a product rule that's involved since you're bringing the exponent out front. So they're very similar. And a lot of books, a lot of times, the final answer, the y piece will be in the front. I always just tack it on to the end. But I know that usually, when they write answers, they'll put that x square root of x out in front. But that's easy enough to find, right? Hopefully. All right. Any questions? So those are the 5 steps. So we're going to do it again with one more of these that have the exponent in the base and the variable in the base and the exponent. And then we'll look at number, why does it say 13? Now I just realized that. It should be number 18 down there. All right, so let's look at 17. Same steps, okay? So let's try these out. So natural log of both sides. So same thing, we're going to expand the right side, bring the exponent out front. So step 2, sine of 2x times the natural log of x. So that's our expanding. And now we're going to differentiate. So again, on the left, 1 over y dy dx. And on the right, we're going to do a product. Okay, so 1 over y dy dx And again, typically the product rules are pretty easy because you don't really get a too difficult problem with your exponent. It's not going to be a crazy function up there. All right, so we're going to start with the derivative of the sine of 2x. So I'm going to write this out, simplify it a little bit. So derivative of sine is cosine, leave the inside alone, and then times the 2 on the outside. So I'm going to put that 2 out front. So derivative of sine of 2x would be 2 cosine of 2x, right? Throw anybody off by doing that? So put the 2 out front instead of in the back. All right, times the second, leave it alone. Plus the first, sine of 2x, times the derivative of the second. So derivative of natural log is 1 over x. All right, so not a whole lot of cleaning up. So I'm just going to get rid of some of those parentheses on this next step. So step 4 is to solve for dy dx. So on this one, I'm going to put the y out front. So again, it doesn't matter where you put the y, as long as you get the y over on the other side. You put it in the front, you can put it in the back. So let's put it in the front this time. All right, and now I'm going to just clean this up without some parentheses. So this is 2 cosine of 2x, natural log of x. Can't really do much with that. Okay, and then plus the sine of 2x over x, right? So we really couldn't do much with those. All right, and then the last step is just to replace y with the original function. So you just got to remember these steps. Again, they're not too terribly bad. And a lot of you will ask me, do I have to do step 4? No. Okay, you can automatically go from, instead of putting a y there, just go ahead and go put the function, and that's what's going to happen. So save yourself a step, that's fine. I don't have to see that. Some of you don't like wasting ink, I know. Heaven forbid, you got to write more steps than you need. So. All right, so there's your derivative. Okay. So not too bad, is it? I hope. All right, now let's tackle the beast down at the bottom. That is number 18, not number 13. All right, any questions on 17? It's awful quiet. All right. Okay, so if I look at number 18, and I would say about 25% of you on the test, if I gave you a problem like this, would just do it by the quotient rule and product rule. And that's fine. I mean, it's not that it's a hard quotient product rule, it's just kind of long, right? I mean, it's, you got to do the derivative of the top, which is a product rule, times the bottom, and then minus the top times the derivative of that, which isn't bad, over this thing squared. So you could do that, just it's going to be long. So that's fine. So that's why I say you don't have to do what I'm getting ready to do. So if you rather do that, great. Just don't mess up on your product rule on the top. Well, what I'm going to do is use implicit differentiation. So right now, I cannot expand this thing because there's no natural log sitting in front of it like, remember this one? This one had a natural log. If it has a natural log, I can expand it, and look how easy that was. You remember how easy that was? So that's what I want to do. I want to make that problem I just saw a natural log so that I can do this and make myself have some easy derivatives. Well, if there's no natural log here, I can put one there. If I put one there, I got to put one on the other side. So that's what we're getting ready to do is our logarithmic differentiation, which is take the natural log of both sides. So by taking the natural log of both sides, I can now expand this thing. Okay? So I'm going to rewrite the bottom. So don't write the bottom out the way it is. Top is good. But the bottom, I'm going to write as 3x minus 1 to the 1/2 power because I need my exponent. So take the natural log of both sides, and now I can expand that right side, and it's going to be a much easier problem. And I'm going to do it in 2 steps. You could do it in 1. Those of you that are good with logs, do it in 1 step is fine. I'm going to just do it in 2, in case you're not good with logs. So, all right, so step 2 is to expand the right side. All right, so first thing, I'm going to break up these logs. The 2 on the top, since they're being multiplied, they're going to be added. and then the one on the bottom will be minus because it's a division problem. So we're going to have 3 terms, okay, 3 terms. Natural log 9x plus 4 to the 7th power plus natural log x cubed minus 5 to the 3rd power minus natural log 3x minus 1 to the 1/2. So anything in the numerator, plus signs, anything in the denominator, that's your subtraction. And they all get their individual natural logs. So we're making this look a lot easier on it. Even though it's longer, the derivative part's easy. So the second step is to take the exponents now and bring them out front. So that's why I said you could do these 2 steps at one time if you kind of remember that. So natural log of y equals, bring the 7 out front of that term. So 7 ln of 9x plus 4 plus, bring the 3 out front of the middle term. So 3 natural log x cubed minus 5 minus, and then bring the 1/2 out front of that. So 1/2 natural log 3x minus. Now it looks longer, it looks worse sort of, but really it's not, because look at what you're taking the derivatives of. 3 natural logs, which are the easy, that's easy derivatives. So no quotient rule, no product rule needed. We're just getting ready to do derivatives. All right. So now we're ready to do step 3. Am I moving too fast? You guys good? Okay. All right, so the derivative of the left is always 1 over y, dy dx. Never changes. Okay. So remember the constants, they stay out front, or they can go in the numerator if you think about it that way. Okay, but they stay out front, and then you're going to do our derivative of natural log, which is the derivative goes on the top, the function goes on the bottom. So 7 times derivative of 9x plus 4 is 9 over 9x plus 4. So you can make that 63 now, or we'll make it 63 the next time, doesn't matter. But there'll be a 63 in the top, 9 times 7. Okay, plus 3, leave that 3 out front, times derivative of x cubed minus 5, that's 3x squared, goes on the top. X cubed minus 5 goes in the bottom. Minus the 1/2. And then the derivative of 3x minus 1 is 3 over 3x minus 1. So yes, it might have taken a little longer, because obviously if you do the quotient rule or you do your regular rules, you can kind of stop after the first step. But this is nice because it cleans it up for you. And if it's multiple choice, it's going to be this way. Okay, so you have to kind of do it that way. All right, so let's go ahead and clean up and move the y over at the same time. So dy dx, I'm going to put the y out front. Okay, so solving for dy dx, I'm just moving the y over. That's always true. And then we'll go ahead and multiply and clean up our numerators a little bit. So this is 63 over 9x plus 4 plus 9x squared. Multiply the 3 times the 3x squared over x cubed minus 5. And then this would be 3 over, now you can multiply the 2 or just leave it. I don't know what you want to do. Let's multiply it since everything else is multiplied out. So 2 times 3x is 6x, and 2 times 1, 6x minus 2. All right, so that's pretty much the answer, except on this one, you got to replace y with this. So your last step, you got to put that thing back in the problem. You have to do that. So that's kind of a bummer on these. But so like I said, a lot of you will go back and do it the old way. And the only reason I would say not to is there's lots of places to make careless mistakes when you're doing it the long way. But some of you don't want to do these steps, and I understand that. Those of you that are real good at derivatives, you don't need to do this. Okay. Phew. All right. So there's your answer.